Welcome to distinct real roots. So recall, if the equation a y double prime plus by prime plus cy equaling 0 had a characteristic equation again, that's just AR squared plus BR plus C equaling 0 with distinct real roots. R1 and R2. Then we got two solutions, or we get two solutions. Y1 equaling e to the R1 times x, and Y2 equaling e to the R2 times x. So the first thing we want to know is, do these form a fundamental set of solutions? So we can find the Wronskian. So we need to know y1 prime times y2, or sorry, y1 times y2 prime minus y1 prime times y2. And we're checking, is this 0 or not equal to 0? Right. So our y1 is e to the r1x. Our y2 prime would be r2 times e to the r2x. y1 prime would be r1 e to the r1x, and y2 is e to the r2x. So we are looking at r2 times e to the r1 plus r2x minus r1 times e to the r1 plus r2 times x, or r2 minus r1 times e to the r1 plus r2 times x. And this is never 0, since we have that r1 does not equal to r2. So what this tells us then is, since the Wronskian does not equal 0, the Wronskian of y1 and y2 is not equal to 0, so we have a fundamental set of solutions. So if we have distinct real roots, we automatically get a fundamental set of solutions, which means all of our solutions are just linear combinations of these. So let's go ahead and work with the equation y double prime minus 4y prime minus 12y equals 0 and find the general solution. So we have constant coefficients. So the first thing we should do is find the characteristic equation. In this case, we would be looking at r squared minus 4r minus 12 is equal to 0. Notice the power on r corresponds directly with the ordered derivative for y in that term. This is r minus 6 times r plus 2. Is that equal to 0? So we get R is equal to 6 or -2. There are two distinct real roots. So we're in our distinct real roots case. So we get y1 equals e to the 6x or e to the 6t, depending what variable you want to work with. Y2 is e to the -2x. And these are form a fundamental set of solutions by our previous sort of work. And so we wind up getting that our general solution would be y is equal to c1 e to the 6x plus c2 e to the -2x. For another example, let's go ahead and solve the IVP. Y double prime plus 7y prime plus 10y equals 0. With y of 0 equals 1 and y prime of 0 equals -11. So again, we need our characteristic equation first. We have r squared plus 7r plus 10 is equal to 0. This factors as r plus 2 times r plus 5 equals 0. We therefore get r could be -2 or -5. Once again, we are in the situation where we have distinct real roots. We have y1 is e to the -2t. y2 is e to the -5t. Again, the differential equation didn't specify what variable we're working with, so you can use t or x as you so choose. By our previous work, these form a fundamental set of solutions. And so we have general solution. Y equals C1 e to the -2t plus C2 e to the -5t. It does not matter which of these you pick as your y1 and y2. C1 and C2 can be swapped as we choose. They're both just constants. To find our particular solution, to the IVP, we were told that y of 0 was equal to 1 and y prime of 0 was -11. So y of 0 equals 1, y prime of 0 is -11. So note y is c1 e to the -2t plus c2 e to the -5t. And y prime would be -2c1 e to the -2t minus 5c2 e to the -5t. So if we plug in 0, y of 0 equals just c1 plus c2. E to the 0th is 1, and this should equal 1. Y prime of 0, we would have -2 times c1 minus 5 times c2, and this should equal -11. So now we need to solve this system. You can do this via elimination, you can do substitution, you can use matrices and do some linear algebra. Whatever technique works for you is fine with me. I'm going to run elimination. So if we multiply this first row by 2, we are looking at 2 times C1 plus 2 times C2 is equal to 2. And we have negative 2 times C1 minus 5 times C2 equals negative 11. If we add these two equations to each other, the C1s cancel out. We are left with negative 3 times C2 is equal to negative 9. And therefore, C2 is equal to 3. Then if we use the fact that C1 plus C2 is equal to 1, we have C1 plus 3 equals 1, and we get that C1 should be negative 2. So our final solution, it would be y is equal to negative 2 e to the negative 2t plus 3 e to the negative 5t. Always be sure that your C1 and C2 are in front of the correct solutions. It's easy to swap which one was paired with C1 and which one was paired with C2. So since our original equation was y equals C1 e to the negative 2t plus C2 e to the negative 5t, we do wind up with y equals negative 2 e to the negative 2t plus 3 e to the negative 5t. So this is how we go about finding our general solution and solving IVPs when the characteristic equation has distinct real roots.